Without further ado, I'd like to introduce Rob de Brincat, who's Business Development Manager for XLAM. Thank you, Rob.
Hello. Is that working? Yep, you can hear me? Okay, so thanks Greg for the introduction. Can I get a show of hands, just get a feel for sort of people who are in the audience today? Have we got architects, engineers, builders, and the others? And there's a lot of others. Who are the others? Building surveyors, yep. Students, yep. Okay.
There's building designers.
Building designers as well. Yep. Okay. Excellent. All right. So it's a good range. Now, what I want to talk about to start with is this concept of thinking differently, and it's really important to understand this. And it's a philosophy that we've developed at XLAM. Other famous businesses have as well. And I think it's really important to look at CLT with a different mindset. We're constantly dealing with builders and designers and plans that come in front of us, and it's a concrete structure, and they're saying, let's do it in CLT. And it's a very much a very difficult thing, even though we are achieving it in many projects, to actually make that conversion. So it's really important to think about this very, very differently. And throughout the presentation, please have that approach, and you'll start seeing why I'm talking about that. So I want to use an example of a business that had this concept, and I'm sure you're aware of who they are. Apple, way back, when Steve Jobs was originally there, before he was removed or he removed himself from the business, had this concept of think different. We've put a couple of different letters on the end to say think differently, but he felt very, very passionate about this, and he really wanted to change the way people thought about using computers and technology and IT. And he really, really pushed it very, very hard. And it was actually a condition for him to come back into the Apple business, that everyone within the business and everyone and the message the business had was to think different. So he persisted with it, and even to this day, the modern logo still remains exactly the same, and they highlight the fact that it's different. And it wasn't until they brought the iPod into circulation, was a great device, but it wasn't until they brought iTunes to link to the iPod, that actually made things very, very different. And now if you look at the way you work with IT, communications, everything that Apple do, everyone is following them now. And everything is so different to what it was back in the 80s and 90s in that space. So they really, really persisted with it. And I believe that the construction industry is still back very much in that sort of era. And there's numerous problems that are existing within the construction industry. And I refer to this quote from, I'm sure you can guess who that is. It says, we cannot solve our problems with the same thinking we used when we created them. So a lot of the problems existing with the construction industry, both in building, design, have been created by the materials and the methodologies that we're using to actually build. Now, you can't solve those problems by thinking the same ways in which you created them. Okay, so you can't look at CLT like concrete and try to solve those problems. You need to think differently. Okay, so that's the sort of message I want to just start with, and for you to understand and start thinking about that while I'm talking. So the first question is, what is CLT? I'll sort of stand behind here. It's probably easy to move some of the slides. Think about concrete precast. Okay, that's probably the easiest way, the easy starting point. So prefabricated timber wall frame as such. So we use it as wall panels. So I've lost a couple of slides there. But basically we're using it as wall panels, floor panels and roof panels. Okay? It is layers of wood that are glued at right angles. So we take standard size panels. I'll show you a bit more of the manufacturing process, and we glue it at right angles. So we have a 3-layer, 5-layer, 7-layer. Some of the Europeans go up to 8+ layers. But we don't use veneers like in plywood, very similar to plywood, but we use solid timber elements. Okay, so at XLAM we run with what comes out of a sawmill as standard, a 20mm, 35mm and 45mm. Smallest panel with 360s, biggest will be 745s, and any combination in between. Europeans run with a 19mm, 22.5, 32.5, 44.5, which is their standard sawmill sizes using spruce. Okay, we manufacture between 15 and 16. Most of the Europeans are around that same sort of size. That's your master panel pressing size, and panels widths up to from 2.2 up to about 3.5 in width. As I said before, it's used for wall panels, floor panels, and roof panels in both commercial and residential construction. I'm not sure why that's gone that way, but these are the slides I wanted to talk about before. There is a standard wall panel, standard floor panel, and a standard roof panel. Okay, so it gives you an idea of that style of commercial or residential concrete precast, but practically made of timber. So it's really important to understand the manufacturing process because there's efficiencies in the manufacturing. If you understand the manufacturing, it's the first line of the efficiency chain. So how's it manufactured? As I said before, we take generally computerised cross-cutting. The New Zealand plant generally does that at the facility, so they get stock in, they'll cut defects out. The Australian plant will actually have that done at the sawmill. Okay, so different manufacturers do it differently. Then it's finger jointed. I mentioned before you have a panel, maximum panel size of 16 metres. You cannot get a piece of timber that's 16 metres long. Okay, you need to finger join it together. However, the width of up to 3.5, you can have that as solid timber. Depending on your manufacturing process, some CLT manufacturers will finger joint everything and will go into a longitudinal pack and will go into a transverse pack. Okay, just for efficiencies in manufacturing. Then it gets planed to size. When I said 20, 35 and 45, generally the raw material will come quite a little bit larger and it gets planed to the exact depth that we want or width that we want, and it needs to be very, very smooth for the gluing process. This shot here is a vacuum press. This is what we use in Nelson, New Zealand. It's I don't like using the word cheap, but it's a cheap of investment to set up a CLT plant by using a vacuum press in comparison to a mechanical press. So basically what happens, you lay the panels out in the bed and you pull a rubber mat over the top, suck the air out of it, gives you the pressure that holds it together for a certain time and glues it together. Same as what you would make glulam for, and as well as LVL is a little bit different, but similar sort of process. Majority of CLT manufacturers would run with a mechanical press. So it's the same process, but it's a hydraulic press that presses it under a certain logarithm, holds it for a certain period of time, and it's much faster and more efficient to do it with a mechanical press. Once it's been pressed, it's ready for machining. So basically what happens is we build a CAD file. Okay, you use HSB CAD, you can use CAD work. There's all these different softwares to use, but we build a 3D model. We generally get an IFC file from a designer. It's always great if there's a 3D model that actually shows where the panels are. We take that and we panelise it and we build a 3D model for every single panel on the project. Every hole, every route, everything. Okay, that's called a CAD. That's the CAD process. And here's an example of a large job we're doing in New Zealand at the moment of the CAD model. Then that gets transferred into a CAM model. Now the CAM model is the main letter here is the M, which is manufacturing, and that's the model that actually allows the machine to cut the panel. So you can see up here you've got different stages. It shows 3 to 8, and you can see that what the process is. There's a cut, there's a saw cut, there's a pocket, there's a lap joint, and it actually simulates it in the model. And it's very different. We use a Wyman in New Zealand. Hundig is another brand. They have different ways of doing this, but ultimately it's the same process. Okay, and that's how we cut the panel. What's really important to understand is we don't press stock panels. When people hear 16 by 3.5, people think that's all we press. And then we cut things out. We actually build the CAD model, and then we nest the child panels onto a master panel and work out how big that panel needs to be to minimise the wastage in cutting. Does that make sense? So that's why it's really important for you to understand when you're designing that what is the size of the panel relative to what a master panel will be to minimise those offcuts. So the Europeans run with standard master panel widths. What we're doing in Australia, and we're the only plant in the world to do this, is we'll have variable master panel widths to minimise wastage. So on a job you run anywhere between 3 3 to 8% wastage from master to child is really efficient. Some jobs are 20 plus, depending if there's curves, certain cutouts. So you can't press an angled panel. You press a square panel, then you cut that angle out. Can you use that offcut? So really, really efficient designs. The designers are looking at what that offcut would be and using it. There's a famous, I think it's a Swiss, they won a competition. It was a little student pod, and the window cut out, they brought it down as a table. There was another angle cut out, and they used it as a part of a bed. And there was it was zero wastage in the CNC process. So it's really important to understand. Then it comes to the CNC machine. This is the Wyman in New Zealand. It does not rain in our facility. This is very typical New Zealand technology. It's to block the shade or provide shade from the sun through the sunlight, through the sunroof. Okay, so the CNC machine has certain restrictions on depth and width. There's a lot of different CNC machines, but when you hear about 5-axis machines, that's what it's talking about. So you can see the axes there. It can rotate at different sizes, and it can rotate in this direction. Some CNCs can actually go completely around the panel. All right? There's certain CNC technologies that allow you don't have to flip the panel to cut both sides. All right? And this is where all the cutting comes into place, and the abilities to cut, route, drill, any sorts of components. And it's very much dependent on the model. It's like buying a car. You get a standard model with certain accessories and you add things to it. Yeah, you get a sunroof, you upgrade your stereo, you do all those things, and you get different tooling, and a lot of these guys can actually design you a tool. So for example, we're getting a 1.5 metre drill bit in our Australian plant, which allows us to drill into the side of the panel 1.5 metres. So if you measure a panel in elevation, we can get a service 1.5 from any side. Yep. This is a tooling, so it's a tooling mechanism. The robot knows that it needs to do a certain task from the cam file, and it needs this router. And it'll rotate, it'll pick it up and go in there and do it, and come back, change it, so on and so forth. Okay? This is same as joinery, but on steroids. So what are the opportunities? The key opportunity is speed of construction. When you're thinking about things differently, you need to understand the speed. And it's sometimes very difficult for builders to, when they're doing their costing model, to actually incorporate that into the model, especially if they've never done it before. But the speed of construction is significant. And this is where the majority of the push is coming on the larger scale and even the smaller scale projects. The lightweight construction, it is 500 kilograms per cube, which is radiata pine, in comparison to concrete precast, which is 2,500. Okay, so the lightweightness is a huge advantage, and I'll show you some case studies later on in the evening of where we've been able to capitalise on that. There's huge design opportunities. Obviously exposing it, a lot of people want to express the panel. What's really interesting, we had a few meetings today talking to people, and there's this perception in the market that a CLT project needs to be this architecturally driven, beautiful exposed structure or building. It's not the case. Yes, there's opportunities for that, but the core business for us in New Zealand is using it as subfloors. You don't see it, it's just fast, drop it in, design it really efficiently to get rid of bearers in your subfloor, and that's generally a very, very core business for us. And the same in Europe, it's houses. They're exposing some of it, but not a lot of it. Okay, so it's just a philosophy around design opportunities, but also understanding there's other practical opportunities required as well. Sustainability is a huge factor. We're as Exclam, FSC, PFC, and we've just achieved Living Building Challenge. All CLT suppliers have this philosophy. If they don't, they're in the wrong game, but we all have this really important philosophy about sustainability. And we genuinely feel quite strongly about it. Us as a business and anyone involved in really the timber industry really pushes very hard. I've come from the commercial construction background, building out of concrete. It took me a while to get convinced when I moved to the timber game. Now I am. When you hear stats about sustainability, that the second most consumed material on Earth behind water is concrete. Consumed by humans on Earth is concrete behind water. That's a real fact. and the concrete industry contributes 5 times more greenhouse gas emissions than the airline industry. So we use heaps of it, and it's causing heaps of damage. Yeah, and it's causing problems as well and creating problems on sites with labour, the amount of people on site, safety, things like that. So there's a genuine push now from the construction industry to actually look at this sustainability, and timber's a clear option or a substitute that can tick both those boxes. Cost of construction is also really important. Let's face it, it could be sustainable, great design. If it doesn't stack up commercially, we won't do it. Unless you've got the client who's plenty of money and doesn't really care about it, doesn't really exist, or it does on the odd occasion. What's really important about costs of CLT or timber construction is that if it's a concrete design and you're trying to convert it to timber, there is opportunities for cost savings. Yes, absolutely. They are minimal. However, if you design it so it can be timber and it's an efficient timber design, the cost savings are substantial. Okay, now these figures are from projects that we've looked at. They're not going to occur on every single job, okay? There's a caveat on that, okay? But when you look at jobs, it's really important to understand the difference between the way it's been designed. And that goes with anything. Yeah, when you're trying to substitute another material that hasn't been designed around it, it's not going to be as cost effective as it could be. So how do we exploit the opportunities? I just want to spend a little bit of time quoting other people in this. Now, I'm not sure if you're aware of this project. This was a job done by Australand at the time, who is now Fraser's. And I'm quoting a professional friend of mine, Case Jong, who was the main driver or one of the main drivers on this project. This was a 5-storey timber frame structure designed and built by Australand down in Parkville, which is, if you know Melbourne, if you know where the cheese stick is. Anyone know what the cheese stick is? When you come off the motorway, one of Jeff Kenneth's creations. It's right near the cheese stick. But it's a 5-storey timber frame structure with floor cassettes. And it made huge success, built it really, really quickly, and sold all the units, and it was a really, really successful project. But what Case said from day one, he said the only way this could possibly work is to look at the structure first. We tend to fall into that trap that the architects and designers want to design their end product, and it's almost robotic now that you know what a 9 by 9 metre grid, what the car parks work with. It works really well with concrete. You know what the thickness of the PT slab is, all those sort of approaches, or whatever the methods are here in Tassie to do that. But if you look at the structure first and actually look at a timber building and look at the structure first, that's where you get your efficiencies. Because timber isn't good at 9 metres. You can get it to work, it's not efficient. So it's got a certain span that works really well, and understanding that span and designing around that span. And people say it means I get small units. Well, there's a lot of architects out there who are designing around that timber grid and getting fantastic designs, and actually looks different to the other competition and the product in the market. The buyers actually walk in and go, this doesn't look like a normal unit. Why is that? And they've worked around a different grid. A lot of people talk about the Barangaroo job, C2, which is Glenn Leese's latest timber creation. And everyone says an office needs to be 9 by 9 metre grid. We can't sell it if no one will want it. And you walk into C2, it's 9 by 6. That's what timber works well with and looks fantastic. Some beautiful glulam columns at 9 by 6 metres. And everyone wants their desk near the glulam column. The second one is a gentleman by the name of Dylan Brady. He's an architect now with Decibel Architecture. He's the main guy there. And this is a job, unfortunately won't get built, but was on Punt Road in Windsor. Beautiful design that Dylan came up with, purely out of CLT. Looks extremely complicated, but it's very simple and extremely efficient. It was about 10 to 12% more cost effective in CLT than concrete. But what his philosophy was we need to design it so it can be timber. Not that it has to be, so it can be. Okay? So then if people get cold feet and want to pull the pin, which happens regularly with these types of structures in early stages, they can do that. And it's not locking them into a certain methodology. Okay? So there's not an issue with designing it so it can be timber, not that it has to be. And this is a slide I like putting up because it's timber, but it shows that this is what I deal with on a daily basis. I've given a circle and I'm asked to put a square into it. Yeah, it's just day in, day out. It's changing. Every now and then we do get a square, which is great, but you're trying to fit a timber design into a concrete design or a steel design. Yeah, so it's really important just to think about that. So you have that opportunity that it actually can work. So there's a few designers in the room, be it architects, building designers, engineers. So I want to talk a bit about the design principles. I'm an engineer by trade, so I always like to talk a little bit about engineering. If you looked at this as a horizontal element, this is a CLT panel, and you were to put a wall below it, even though it looks like it's drawn above it, let's assume it's below it, and you would analyse the CLT panel. If you analyse it in the green direction, okay, it's very simple. You basically allow for the timber, or the cross-sectional timber, where the grain is running in that direction. If it's running perpendicular to that, it's purely a spacer. It's not doing anything. It's just a lever arm for when you're calculating your stiffness, almost like the web in an I-beam or a steel beam. The flanges are doing all the work. Okay. However, you've got a small cantilever off the edge there, right? And that's the red direction. You can actually now revert 90 degrees and allow for the timber, where the grain is running in that red direction, as also a beam, and allow for it to span in two directions. Okay, it's much smaller. Okay, the lever arm is shorter, but it's got less stiffness, but it also still has capacity. So a lot of the designs in Europe in CLT have a lot of the columns offset into the building and allowing this little cantilever off the edge to work. Okay, it's really, really an interesting way, an important way to understand. Now, I'm not sure if is anyone aware of this project? The Hang House in Austria. I'll talk about it in the case studies, but I always thought for about 3.5 years I kept calling it the Hang House because it looked like it was hanging, but apparently in German hang means cliff. So I was talking nonsense. But the reason I put this up is this is a two-way spanning slab system where you can see here the only thing supporting that slab are the columns. There are no beams. The beams are the timber within the CLT spanning in that direction. Okay, so you've got enough timber running in that direction, you've also got enough timber running in this direction, inclusive of the cantilevers on both ends. So from a design perspective, you can actually achieve some pretty slimline looks in adopting this philosophy. Now this is quite a complicated connection. It's not something you do on a commercial job. It's more high-end residential. There's a bit of money available, but there's 3 panels here. All right? So you can imagine those panels sitting like that, and right in the middle there, it wants to hinge. Yeah? So what you do is you actually screw that connection together on angles, and it's quite a stiff connection and allows about 90% of the moment to transfer between those. Okay? So this is the sort of opportunities you can get using timber and CLT. The same philosophy works for a wall or a beam, or when you've got timber running in the horizontal direction of a beam, it's actually working as a beam. You've also got timber running vertically, that's actually working in compression. All right, so the majority of them are working horizontally, it's a beam configuration. If majority are working vertically, then it's a wall or column or compression component. This is how lintels work. So you look at the one on this side, you cut a doorway out of it, there's timber going across the doorway, that's your lintel. Yeah? But you can also use a wall as a beam. So this is another example of it where this panel here at the base is one piece, and it's actually got a backspan, it's cantilevering out and holding up the balcony. Yeah? So when you use these two philosophies, it gives you an opportunity to actually do different forms and shapes from a design perspective. Fire. Fire is a very important component when you're talking about timber. It's the most commonly asked question. It is the burning question. And ultimately, look, the answer is actually quite simple. Timber chars when it burns, and you can calculate that char based on the species, and you can work out what is left after the fire period and work out whether that is actually adequate to hold the reduced fire load. All right? The main concept here is that it's not sticks of timber. You want to start a fire, you don't grab the biggest, heaviest log you can find and try to light it with a lighter. You grab little kindling and get that going, and then you start throwing the big logs on. Yeah. So the same concept exists with CLT. XLAM as a business, we've done full-scale testing with basics over CSI erode, protected, unprotected, and we've got all that test data. So it's all available, it's all in accordance with Australian standards. But to understand it, it's some key points. There's four. Floors tend to have a high inherent fire rating. Okay, the reason for that is the design is generally governed by dynamics and deflection, so you tend to have a bit more meat or timber on the floor, increases your ability to char. Okay, walls need a bit of help under high load. Right? A wall itself can take huge amounts of capacity, but as soon as it starts burning and you lose that outer layer, it can go to custard. So a lot of walls you design are actually 3-layer. We're looking at jobs that are 12 stories, some of them with short spans. The walls at the bottom are 125 thick, 3-layer panels. Easily take the load. But then it starts burning, that outside layer goes and the thing just falls apart. So adding 16mm fire check to it or a fire rated plasterboard creates enormous extra capacity. So it needs a bit of help in that sort of area. That fire rated plasterboard can do a lot more than you think. Fire rated plasterboard in industry for 60-90 minutes is generally tested on stud walls. And what fails before the plasterboard is actually the stud. Heats up to a certain point, it's thin metal and it buckles, and that's what causes it the wall to buckle. When you're fixing it to a CLT panel with long screws, it hangs in there for a hell of a lot longer time than you could possibly imagine. And it gives insulation, and it reduces the charring to significant effect. And our test data proves that. The other point is the devil's in the detail. That's with anything, but when you talk about penetrations, fire doors, lift shafts, fire stairs, they're the detailing components, which the CLT supplier and designer should be able to assist you with that. The other component is acoustics. And look, long and short of it is that there's the Wood Solutions, FWPA, have constructed and implemented the most advanced acoustic testing ever done in the world with CLT. XLAM were involved, Stora Enso were involved, Binderholz were involved, and someone else who they never told us who it was, but their panels were there, were tested. Everyone contributed. FWPA threw half the money in, and we tested it, and every one of those suppliers got enormous amounts of data. And other companies like XLAM are actually taking it to another level, developing software, so on and so forth. So there's solutions for acoustics, for walls and floors, for a range of different applications. Okay, I want to talk about the design and construction process and efficiencies in that as well. Just keeping an eye on the time. CLT fits in that prefabrication element. Okay, prefabrication is a bit of an open-ended term. Doesn't mean you need to have a full module finished, delivered to site with the forks and pictures up on the wall and the linen already in. You can have prefabrication to a point where the construction is actually pre-thought of during the design process. And this is probably one of the biggest challenges we have with dealing with builders, is that they constantly ask the question, why are we talking about the switches now? Why are we talking about electrical now? It's because we want to be able to route that in during the manufacturing process. So there's a job I'll show you a bit later, which was 3 towers in Western Sydney, where the builder said the amount of money they saved in chasing during the CNC process compared to doing it on site was extraordinary. Worked out about $2 a square metre. Full chasing of every service during the CNC process compared to what it would cost during the actual construction side of things. So it's all about understanding the difference between traditional construction and prefabrication and how that it's more heavy in the design and faster on site. Okay? This is the efficiency chain, let's say, and these are the areas that we need to get efficiencies in. This goes for any material, but it probably needs to be reinforced when we're talking about new materials like CLT. So it's design, manufacture, transport is really important, and obviously construction as well. If you can tick all those boxes, you're getting an efficient design. So let's talk about just quickly transport. This is an area where it's really important to understand this process at the start or during the design phase, because when we cut these panels, it's like precast, you need to know the order in which they're going in. So you can't make a panel that's 16 metres wide and say, I just put it to the side and we'll use it because that's level 4, you know, and then level 3 comes out and you're trying to sort all these things out. You need to know the efficiencies. You need to be able to put it on a truck so it turns up. We're not dealing with precast where you put 2 panels on, we're putting 20 plus on. Yeah, you don't want it to turn up on the site and the builder goes, mate, I need that one in the middle. We've got a problem, yeah, because you eliminate that whole speed of construction. So this is an example of what we'll do in the modelling process. We'll actually model the install, and then on 100% of projects in Australia so far, until our plant's operational, there's a container involved. So it brings another level of complexity to it. Fit in a container in an order in which you can then put it on a truck efficiently. Lendlease, when they built the Forte building, had to empty all their containers and restack them. Yeah, so it's a bit of a, I'm sure that didn't come up on the spreadsheet on their costing analysis. Value add is also an important component and a really big opportunity for CLT. And it's existing, and a lot of builders really want to push this. It's about adding value to the panel or the end element, be it CLT or anything, in the factory, under a controlled environment. So when it turns up on site, there's less to be done. So it goes back to the original slide of reducing that on-site construction time. So this is some of the things we're doing as Exclam. I know that a lot of the Europeans are in this space. A lot of the timber industry is moving to this space as well. Pre-cladding, putting windows in. This is stuff we're doing in New Zealand, but also looking at setting this stuff up in Australia as well. Standard connections, not standard, I shouldn't, that's not very standard, but you know, that's very difficult to do on site. Yeah, let's bring it together. Let's do it in the factory. Let's put some of that structural steel in and get that a lot more efficient on site. So, ask the question, why not CLT? If all these great things are here, you know, there's huge opportunities. Let's capitalise on them. There's all these advantages. Why aren't we building heaps out of CLT? And we're not. There's a lot of factors. There's the big container issue, trying to ship it in, lead times, risk. All of those components, termites, fire, acoustics, people needing to understand and get confidence around this. And I mentioned the word before, it's about risk. It's about reducing that risk, okay? Because, you know, there's builders here, and I know what crosses their mind when they look, do you want to build this out of timber? I've never done that before. That's a high risk for us as an individual, as a business. We've never done it. We've done concrete day in, day out. We know the costs. We know the process. We need to help reduce that risk as a business, as an industry. And part of that is about the decision Exclam made to build our facility. Okay, now one thing I didn't change on this is that bottom figure. It's probably getting close to $40 million now as an investment for our business to build this facility. Okay, to give you a bit of an idea, it's about 12,500 square metres, 60,000 cube capacity is stage 1. To give you an idea, the Forte building was 1,000 cubes, which is a 10-storey apartment building. Okay, so it's very big. It's in Albury-Wodonga. The whole concept, it's made of, it's going to be using Australian-grown plantation radiata pine, and the whole objective to the team was to build a globally competitive and the most technologically advanced CLT plant in the world. Okay, and we believe we've achieved that. We'll confirm it when we turn it on, but that was the aim, and we believe we're well and truly in that process. So there's some shots of the construction. The facility is finished. The first of 66 container turns up in, I think, 3 weeks. So it's well and truly underway with all the plant and equipment in it, that is. So these are some shots of it. It's, I don't know if you know Albury-Wodonga, if you've ever driven up there, but that's the big Woolworths. It's at Logic, the Logic facility there. That's a big Woolworths cold storage facility on the left. Yep, your left. Some shots of it. This is probably the best one, which shows the CNC bed. So that's where the CNC machine will go. This side of the factory is all the pressing and planing and gluing. That little square over the end, it's a little one, but that's the press, mechanical press. And then the gap in the columns is where that 16-metre panel can actually slide between the bays and go from the pressing and prefab into, sorry, pressing and pre-works into the actual CNC. And it has an option to bypass the CNC because some people want to buy just blank panels off us. All right. First project I want to talk about is hot erode in Exlam. It is supplied in Exlam, but it's in New Zealand. We kind of like calling this project sort of our Sydney Opera House. So I'm not sure if you know the history behind the Sydney Opera House, but it's deemed a very successful project. But if you look at it from a project management perspective, it's not a successful project where you blow budgets, you blow programs, you do everything, but it's a beautiful structure and it's a signature structure. This is a job that is very unique. It's a studio. We've won enormous amounts of awards on it, and it really does push the limits of CLT to a degree, but it gives you an idea of the capabilities and design that you can achieve. There's another job I'll talk about a bit later which pushes it even further, which is a job we're doing in Sydney at the moment. So it's a small job, 45 cubes. What was really quite fascinating about this is that the build time to put the CLT up was just over a week. So even that, with that uniqueness, all the design and all the thoughts actually been put into the design process. So it all been thought about and goes together really, really well. All internal panels are visual quality. So every CLT supplier has different grades of visual. It's basically like plywood. You just select a grade, and it depends on the species of timber and the knot sizes and defects. It's very different across the entire range. But not one panel on this project was square or identical, and every single one was visual quality as well. So you could see the challenges associated with that. And the detailing was quite extraordinary. Some of this is clad, but what's really, really fascinating about, or really a huge advantage of this type of system, is that even though you want to clad it, you can actually design the shape behind the clad during the design process. It makes it a lot easier than trying to build this with stick timber. And it's very difficult to be able to understand a design in 3D when you're trying to build it, rather than doing it in a model and letting a robot cut it into shape. A lot of detail is put into the surfaces. You can see routed trim lights there. You can see a lot of the surfaces are running either through holes at the base of the panel in this triangular shape, or through the back of the panel. But that's one of the visual quality options available from Exlam. It's one where we're sort of considering at the moment, because what it actually does, radiata pine grows with the nodes or branches at regular intervals. So you can actually cut all the knots out of radiata pine and glue it together so it's knot free. It kind of goes a bit against the whole sustainability thing in my view. But you can see here, you can see the finger joints. You can see where the grain changes along the panel. So some of the finger joints are actually this big. Yeah, so it's an interesting approach. You can also notice there and I think the next shot shows it. You can see the shadow line detail between the walls and the roof. And that's how it was achieved with a pre-installed rubber strip that sits on top of the wall that accepts the roof panel. It was cladded in an external timber cladding, and a zinc roof sheeting cladding was used as well. So quite a unique style structure, and I think the main message here is it shows you that you can get that sort of form in your design and control that through the CAD, CAM and CNC process. The next project I want to talk about is Beeley Ave Backpackers. This was the largest CLT project in New Zealand at the time. It was the biggest job Exlam had ever done, and it was a low budget backpackers facility in Christchurch, built after the earthquake, so earthquake design was obviously important. 540 cubes and the structure built in 4 weeks. This is a very traditional CLT structure, very, very efficient, hotel style layout. They're very repetitive, all the panels are the same, short spans, continuous spans, with a corridor down the middle. And being able to use these types of walls for bracing. So you get a lot of walls going in both directions. So from an engineering perspective, it's a very stiff box. So we're looking at a lot of student accommodation buildings where you've got that sort of layout for 10, 12, 14 stories. It's very, very stiff. So it's just the CLT a lot of the time is adequate to provide the structural layout of the building. This is the a shot of the model. It shows all the panels, gives you some stats, 5,500 square metres, all broken up into 15 deliveries and install times. This is a sequencing, so the model that would be generated by any CLT supplier, where they model the stages and what panels. You can link this to the truck, so you can have a document that says truck number 7 has turned up and it's got these panels on it, and this is the order, and here's where they go on site. To the level where the Hundigger CNC machine we want to put in the Albury will have a QR code printer, so it can actually have a master panel put down. It will print QR codes on, knowing where all the child panels will be, cut it all out, and it'll have a QR code on the panel, which on site you can scan it and it should bring up on the model where that panel actually goes. So that's the sort of technology we're trying to... Sounds good in theory, we'll see how it goes when we try to do it. This is a shot of the subfloor going in, so a lot of New Zealand subfloor because of the earthquakes, especially in Christchurch. What's really interesting here is this pre-cut services. So having those cut in and dropping that on top of the services under the subfloor. Yep. Again, all good in theory, but you need a good plumber who puts them in the right spot. Yep. Because you can tend to have an issue, or it's not an issue in drilling it on site. Yeah, it's all about what's suitable, and it's possible because it's timber. You can actually obviously drill it inside as well. Just a sort of panoramic view of the walls going in. Yeah, you can sort of see the size of the panels and the propping requirement until the floor goes on top, and then it's screwed off and the props can be removed. A really interesting detail here is part of the earthquake connection. This is a castellated joint where we actually cut a sort of a nib out of the CLT panel, and it locks into the floor. So it actually creates a very, very stiff connection. Our engineering team come up with this, worked with the engineers in Christchurch, and our production people were kind of like, well, that's going to take a bit of time to make. There's a bit of wastage in this as well. So it's about understanding the design, linking it to manufacturing and that whole efficiency chain we spoke about earlier. But a really, really efficient way of eliminating the bracket connections required to transfer the load from the floor into the wall in that earthquake system. I think I've showed this shot before, but it's a really good one showing the floor panel being lifted in. One of the many lifting methods. So pre-drilled holes slung through. A lot of the time those slings come pre-installed. We also have ferruled bolts. You can screw into the top of the panel and lift off the top of the panel. There's all different methods of lifting as well. They actually went with a non-visual product but exposed it. So this is just a touch over non-visual. All right, so you can see the knots and defects, which is quite common in radiata pine. It gives you an idea of what that looks like, and also in one of the rooms. What was interesting with this is that they actually, one of the beauties of running with a vacuum press is it is labour intensive, not like a mechanical press, but you can have the ability to sort of leave gaps in the panels. So what you do, that outside layer is going vertically, horizontally. What they do is they leave a gap at a certain depth, and that allows services to be fed through. Yep. You can't do that in a mechanical press. You'll lose an arm. So that's one of the advantages of having a vacuum press and being able to do things like that. An advantage for us as a business is that we're going to have both options. Have the grunt of a Wodonga plant and probably the delicate approach that could be done with a vacuum press out of Nelson. Another example of that is a company called Binderholtz. Binderholtz run both. They've got a mechanical press, and they've also got vacuum presses. Okay, they're probably the only Europeans that run with that sort of option. Majority of the others have either a vacuum option or a mechanical option. So this is now the largest job in New Zealand, which is Otago Polytech. It's a student facility. A really big job 4,500 cubes, which is quite substantial. So it's over 4 fortes. And again, you can see that connection detail through the earthquake requirement in that region, and it's got pre-installed plates as well. So it sort of shows you the level of detail that you can achieve. We don't need to really do this here in Australia, but it shows you the ability of the CNC. You can see the accuracy of the cuts here, trying to fit that all in. It's quite unique. It's a job actually under construction at the moment. There's the model. And if you can't really zoom in on it, but you can sort of see the slots and the penetrations and everything sort of cut in along some of those lintel beams across the top and the castellations at the bottom. So it's a very, very detailed model that we develop. And some shots there of the slinging, the way of pre-installing some of these steel plates and that whole rivet approach. And you can see some of the connection details along the walls there as well. And there was a fair bit of LVL in this, so we're actually doing, it's really important to understand that they all go hand in hand, and that a lot of CLT suppliers around the world, a lot of them actually generated as originally as glue lamp manufacturers, and then they moved into CLT, and they tend to package that up and supply that. So, if there's glue lamp in the project or LVL, we look to partner up with other suppliers, and the Europeans will do the same or already have supply in-house. So they very much go hand in hand. And this is some examples on this Otago Polytech job of steel being incorporated into it as well. And XLAM as a business actually supplied that whole package, pre-installed bolts and connections and things, which we see is really important. I think the whole industry needs to do that, and I think one of the issues with the timber industry is that a lot of the suppliers have sort of wanted to just supply timber and not sort of give that prefabrication element to it. They've done really well to do that in the domestic space, but when it comes to commercial, they tend to like dropping packs of timber off and letting the builder do stick building. So you really need to understand this and be open to offering that solution. I wanted to put this in, and it was only after I had a meeting this morning. This is the one that we're talking about, what the core business in New Zealand is, and this exists in Europe as well. And there's this misunderstanding or perception that it has to be this huge, big job. I think I said it before, but this is a job which is just a house in Nelson. Timber frame walls, CLT floors, and roof. Okay, look at the timing. The lower floor or subfloor was installed in an hour. The upper floor was installed in an hour and a half, and the roof was installed in 2.5 hours. So it's really, really simple, and it's basically substituting a flooring system. Now, I'm not going to sit here and say it's going to be cheaper from a material perspective than an I-joist or a posi, because it's not. It's going to be more expensive, but the speed of construction and the efficiency on site and the performance of the floor significantly better. And they drop the wall frames on, with then the subfloors coming in, and also with the roof. Okay, so it's really important to understand that the biggest industries in CLT in Europe as well as New Zealand, Australia has sort of fallen into this trap, and so have the US. It's all big jobs. Now, the first job we ever did in Australia was the world's tallest timber apartment building. Everyone thinks that that's what you need, that's what CLT is. That's not. Yeah, so we've delivered 350 projects in New Zealand as XLAM, and majority is that. It's bread and butter. It's easy stuff. Builders love it, and that's what we're really trying to promote here in Australia as well, because prior to us being able to set up an Australian plant, everyone's been talking about you wouldn't get a subfloor imported from Europe. You just wouldn't do it. It's too hard, too much effort. But what it allows with the local manufacturing and local supply, it allows those opportunities to happen. Builder would love to be able to get the subfloor in, not have to get increase his crew by a certain amount to stick build it, or it's on a slope and it's a pain. Let's just get a subfloor in of a CLT product. So I really wanted to sort of have a chat about that project, which I'm glad I put it up now. So this was XLAM's first ever Australian project, which was in Tasmania at the UTAS student accommodation, which Greg was heavily involved in. where CLT was applied as the floors to all the common areas on a supporting steel structure, and also as a stair system. So we had supporting steel frame, and then the CLT sat within the web on quite a substantial span. So we had quite thick panels there, and worked really well. There were some detailing issues around the steel because I remember getting the phone call from Hutchies, who were the builders, saying, "Your panel's wrong. Your panel's wrong. It doesn't fit." I said, "Have you measured it and cross-checked it to the shop drawings?" They said, "No, we haven't." I said, "Well, let's do that before you yell at me." And they measured it and said, "Well, it's within 0.5 mil." And the steel was out. But the whole design approach to that was the steel ever going to be in? On that angle, was it ever going to be within 1 mil? It's not practical. It's not fair to sort of expect steel to be that accurate. And that sort of shape was, that interaction between the CLT and the steel was probably the biggest challenge. But ultimately a good success, and the best result was Hutchies turned around and said we should have got rid of the steel and done it out of timber. Would have been a lot easier. Corridors, so these are all done out of timber modules, so all of the unit shells, and then CLT was done in the common, so you can see here in the corridor areas. Here's a shot of it from the front. And the stair system. Now that was probably the biggest success of the project from our perspective, were the stairs. The builder, Hutchies, were, let's say they were a bit nervous about it, to say the least, because stairs need to be very accurate. And they're used to doing concrete precast, so we were saying, look, it's going to be okay. They stood each stair up in a day and a half, and they allowed over a week. So you can see that central piece, which is this piece here, and that piece going through, is one piece. So it's one piece that drops down the middle of the stair with the triangles pre-cut out of it, which acts as the balustrade. And then the stair rises and landings were sort of dropped around it. So the balustrade was pre-drilled on the opposite side in line with the stair riser. So they just didn't have to measure it and look on the other side, where's the stair? Just drill it in. And it fit like a glove. So we're really, really happy with it. And it's something we believe when you compare this floor, any CLT stair, to a concrete stair, it's significantly more cost effective. Okay, so it's a really, really big market for us. And a lot of architects are using it as an exposed feature. It's another job. This is it's under construction at the moment. Kane Constructions are the builder. NH Architecture, Monash University, and Bollinger Grohmann are the consultants. So it's a 2-storey vertical extension on top of an existing 10-storey building. Or is it 8? Anyway, it doesn't really matter. Reason it was selected because of the lightweightness. So there's a steel grillage, which doesn't really show it, but underneath that floor, you can see some of the steel coming up, is a steel grillage transferring the load of the auditorium structure through the existing structure, okay? And the reason CLT was used because they didn't want to have to upgrade the structure underneath. And it was the only solution they'd come up because of the lightweightness of it. All right, so it was steel grillage, CLT floors dropped on top, and then the CLT walls installed as well. Some glulam beams, which they're covering up. They're hardwood glulam beams supplied by Hein, beautiful pieces of wood. Trying to convince the architect to leave them exposed, but they're going to cover it all up. And the roof structure as well being CLT on top. So that's the roof, which sits on top of the glulam. So really simple structure. There's a stair, which is a feature. So this is being exposed by the architect, where you can see one of the stair elements being dropped in by crane, and it's not finished. We've got some finishing work to do there, but you can sort of see the CLT balustrades, stairs, which are getting some timber put on top, and exposed walls as well. And there's another shot of it. Yep. So quite a nice feature. This is probably our new Sydney Opera House. This is a job designed by James Fitzpatrick. Does anyone know James? No, he originates from Tasmania. He's a leading architect in Sydney. His job's in Castle Craig. It's his own house. So James's strategy here, or philosophy, is to push the limits as far as he possibly can. Wait until it almost breaks and push it a bit further. So these are huge cantilevers coming off. This is artist impression. You'll actually see a bit of extra steel put in there because it just couldn't get it to work engineering wise. But there's basically four rectangular tubes that come out and cantilever and anchored back on a concrete base. The floors, you can see here, the floors actually are spanning perpendicular to the cantilever, and what's actually doing the work are the walls. The walls are acting as beams. What makes this even more challenging is that everything is exposed. So all the fixings need to be either inside the timber or on the outside of the timber, which to any engineer will give you headaches. But this is a sort of concept, very, very thick wall panels that are coming out and connection details underneath. Just show you some of the construction details or shots. Some really, really lightweight props as well, and you can sort of see the thickness of the panels. And details such as the recess. So you can see it being recessed, the panel comes and then gets cut out on an angle because the roof then comes down all exposed. So all of that can be detailed within the CAD process. There's also chamfered edges on it. Okay, you can see the panel coming out and there's a chamfer. So the panel comes out and there's a chamfered edge, and they're all chamfered out, as well as the floor panel. Okay. This is the cantilever. So you can see a bit of steel in there now, just to make it work. It gives you an idea of and you can see the connection details. See the connection details on the outside. What the pink stuff is the wrapping, the breathable membrane. So what's great about CLT, you can actually use adhesive wrap, so it's actually sticky. You couldn't do that on timber framing because it will just be sticky everywhere and I'd be sticking every stud. With this, actually, it's almost like wrapping back at school when you wrapped your workbook. Very similar, but wrapping timber. And it really creates a really, really good barrier and air tightness around the structure for its performance thermally. So James has got a drone that flies over the top of his house. So you can see the CLT structure starts right at the front and works its way back, or starts at the back and works its way forward. So you can see the tubes coming out. There's a really complex steel truss sort of on the third box back, and that circle component is a spiral CLT stair that we're installing as well. It's a shot of it. That was a shot only probably about a week ago. To speak to the builder about loading up those panels as much as he's loading them up. So it gives you an idea, and it's still got probably another 12 months of construction, but it gives you an idea of the capabilities of CLT. So I like showing this, but please don't ring me and say you want to build one exactly the same. But there's ways of actually becoming still getting a similar look, but making it a bit more efficient. So this is the hang house. This is a job delivered by KLH. I had the pleasure of sitting down when I worked with KLH with the engineering manager, who worked very heavily on this project, and I found it completely fascinating how they achieved it from an engineering and architectural perspective. But I'll show you some images of that, which will sort of paint a better picture. So they put the steel posts in and then had temporary propping. Okay, so it's really important to support the panel before you screw it all together. Yeah, because as I said before, it wants to hinge. And you can also see there, it puts it in perspective how big that panel is, how much timber is running in both directions to get that two-way spanning capability achieved. And this is it dropping in. So you can see how they've notched the top and bottom of the panel. Okay, and that's how they screw it together. So basically what you're getting is you're getting a screw about that long and you're screwing it on an angle through both panels. So they come together and you're screwing on an angle through at certain centres. Okay, and that's what's giving that stiffness. Then what they do is they apply like an LVL or a hardwood splice on top and then screw that down. And that's what's giving you the stiffness. So it can span. Some shots of the panels going in. You can see there it's a 1, 2, 3, 4, 5, 7-layer panel. These are the splices. You see the timber cladding on the edge of that splice being screwed in, and the propping still in there. So once that's all screwed off, you can then remove the propping, and you end up with the finished product. So there's a couple of shots inside. You can see that splice detail. Whether you like that fully exposed, a lot of people call it like a sauna, but in Europe it's very popular. And it would cost a lot more money to actually look at that ceiling exposed with all that engineering connection as well. So if you were to drop a ceiling in it, you wouldn't need to be looking at that splice as being a visual component, things like that. What also is really interesting about this is the floor-to-ceiling glass. So it just gives you confidence about how thick that panel is and how it's actually working. And you know, the ability for that cantilever, two-way cantilever to move and having glass in that area. Yes, that's obviously really important. There's some detailing issues with this job. KLH had concerns with it. Exposing, edges and things. You need to protect the timber. Okay, so it's not, you can get there can be a misunderstanding of that you can just expose it. You actually need to protect those edges, because if water gets in those edges, you start having issues. But they've cladded that. If you look closely, it's actually cladded in timber. But I know that there were some issues there from KLH's perspective on how it is actually detailed. But nevertheless, still a very, 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 very good project. So this is the Stutt House in Murray Grove. Is anyone aware of this project? It held the title of the tallest CLT or timber apartment building in the world before Lend-Lease came along and built the Forte building. It was basically the same team. So KLH delivered this project, and Lend-Lease employed KLH UK, Karl-Heinz Weiss, and the team there to assist in the design and supply and construction of the Forte building. So there's a huge amount of similarities between these two structures. It's really important about this. It's 9 stories and 7-week CLT construction component. So you can see the KLH guys there. They're Austrians. So they brought an Austrian installation crew in to drive the panels from Austria to London and to install them. So that was 7 weeks for 9 stories, and they weren't driving on the weekend. So they spent 1 day a week driving the panels to site. So we could have even achieved a lot more efficiencies in that install as well. So they'd get up on early Monday morning, drive down, get there by Monday night, install, and would push hard to try to finish by lunchtime on Friday to get back in the car and drive back to Austria. So this is a very traditional connection detail. You can see the screws the brackets being pre-installed in the wall layout areas, then the walls getting dropped in and screwed on in that detail. The Europeans adopt a concrete screed approach. So they screed the floors, and that allows them to put floor heating in, gives thermal mass to the structure. It also hides the brackets. It helps with acoustics and dynamics, okay? Which has always been the approach when it came to Australia as well. But all our acoustic testing actually shows you don't need the screed. The first thing the builder wants to pull off is the concrete screed. They constantly say to me that that's why we're looking at CLT, Rob, to get rid of the concrete. So don't tell me I need to put concrete on it. So it's an example of how the Australian industry has really created details that don't really exist anywhere else, because they want something different and it needs to fit the market here. All the lift core and stairs was all done out of CLT as well. Okay, so they run with a double skin, which is the same approach that was done on the Forte building. You can see it there. They run with a double, so they've got an internal lift shaft wall that spans about 2 stories. So it actually comes in and becomes the balustrade of the level above. So it cantilevers up. and then they bring the internal unit wall to it, and there's a gap in it with insulation for fire and acoustics. And that's how they detail it. It's a bit more complicated than that, but that's the basic principle behind it. And what's really interesting about this job, you could not see a stick of timber. Completely cladded, belt and braces approach. Purely from a conservative perspective, trying to get certified in London, being the first major timber apartment building, basically covered it with double fire check. Every bit of CLT had 2 layers of 13mm plasterboard on it, okay? Which is a massive overkill considering what I said before about the charring ability of the panel. So moving on to the Forte building, which I'm sure you're aware of, an extra level and an extra 3 weeks. So that's probably the Lend-Lease factor on that. So that was the tallest timber apartment building in the world. It was recently taken over by the Norwegians, who built 14 stories, and now the Canadians are over 20. And the Austrians are, I think, 24 is coming up. So that's why Lend-Lease have announced the Brisbane job, which is going to be the tallest commercial building in the world. So they just keep, competing against each other, let's say. So you can see very, very similar type of structure. You can see the lift shafts. So the same philosophy was done with the lift shaft. You can see the panel sticking out. Very small project for a company like Lend-Lease. So it's very much a pilot approach for them. I don't know if you know Melbourne, but this is in Docklands. Docklands is down near Etihad Stadium, sort of down that bottom part of Melbourne, and the grounds on Coot Island silt is really, really bad foundation. And a lot of buildings in this area don't have any basement car parks because it's just slop. So what Lend-Lease actually own a lot of land there, and the whole philosophy was they were looking for a lightweight material to build multi-storey buildings out of. And that's where they come up with the CLT approach. And they use this as a pilot project just to make sure that they got their systems and procedures in place and that the market would actually buy it, which they waited for complete construction construction and finishes to be completed. Then they went to market and sold it like they would sell any other building. You can see the lift shaft going in there, remote control crane. So one of those rectable cranes that can be remote control purely because of the lightweightness of the panel. What's also interesting here is that the pre-installed brackets and the confidence in the system that it's actually going to fit really tight. So if that was concrete precast, I'm sure there'd be a bit more of a gap there just to make sure we can wedge it in and get it in on accurately. So, or you put the panel in, then bring the bracket to it. So it shows you the sort of accuracy level that you can achieve. A little bit difficult to see, but they've got a double CLT wall as a detail between units for acoustics. In all the jobs we've looked at, it's an expensive approach. So we're looking at generating that separation being a separate stud wall. So all CLT up and then building a separate stud wall. But Lend-Lease took the approach that they didn't want to build any stud work inside, so all walls were CLT to speed that construction process up. What's really interesting about this is that you look at the progression from the Murray Grove stud house to Forte and the exposure of the CLT internally. Yep, so Lend-Lease did a really good job to take it to the next level, where they're actually exposed internal load-bearing walls as well as the soffits for the balconies. And look, I think it looks quite nice, just that not too much, it's not that sauna look, but at least exposing and expressing some of the CLT as well. And we're working on jobs now where the architects want to take it even further and further to the point where there's jobs they want to expose the whole, 10-story buildings, expose all the CLT, which is a challenge with the fire brigades, but nevertheless it's evolving the way the boundaries are being pushed. So these were the two key starting points for Australia in CLT. That was the Forte building and the Docklands Library, which was just down the road, also done by Lend-Lease. CLT was adopted because they wanted to, I believe there's a job in Hobart where it was a hotel built on top of a wharf, where they wanted to maintain the existing wharf structure and not have to upgrade it. Exactly the same thing happened with the library. Okay, so the lightweightness was a huge advantage on both of these projects. So since then, quite a few CLT projects have been built. There's more than what's on that list. There's UTAS down in up in Launceston. There's 3 towers in MacArthur Gardens, which is the top left-hand corner, built by Strongbuild, who have an alliance with Binderholz, who are a European supplier. You've got Barangaroo, which is Lend-Lease's recent creation, and they're also building one up in Brisbane, which is, I believe, 10 stories. That's starting construction very soon. That's supplied by Stora Enso. You've also got this job in Adelaide, which is Kent Town, which is La Verde Apartments, which is 3 stories on top of a 2-story concrete structure, a mixed-use development. So that's approaching completion in Adelaide as well. And there's also a job in Melbourne, which is starting the design process this week. It is it's an existing 6-story office building, and they want to put 10 stories on top of it, a hotel out of CLT. So the philosophy around that was that the structure was always designed to take an extra 6 stories of concrete. And then we approached the developer, myself and Nick Hewson, our technical manager, who was at ACOM at the time, and said, look, if you did it out of CLT, you'll get an extra 4 levels without upgrading the strength of the structure. So they were obviously interested in that, and it's taken about 3 years, and now we stand here looking to build that out of CLT, all approved. So it shows you the sort of projects that are happening. A couple of big jobs in New Zealand. You've got Otago Polytech. There's another job in Auckland, which is a student facility as well, and Auckland Airport. So Auckland and New Zealand's really taking off as well in that large-scale projects. But just to sort of start the conclusion, it's really important to understand, what the evolution of CLT is in this country, and it's actually opposite to that. So as I said before, we started building the world's tallest timber apartment building. Yep, and we've got to kind of learn to run before we walk. And a lot of people come to us as a business and the Europeans and talk about building a 14-story, enormous 8,000 cube project. And you'd be surprised how many of those we've actually got in the pipeline. But what's really important to know is that we're here to support those small-scale projects, right? To look at, even if it is just a subfloor, a small-scale project, that is the reality now. With an Australian plant, you can do that, and you can design those, and we can supply those sort of projects. And it gives people confidence in that whole journey of understanding a new system, the risk associated with it, that, I really encourage you to start looking at those smaller scale projects, just to sort of dip your toe in the water, and we can support you on that. So it's really important to understand how it's evolved and how you can get involved in this sort of area as well. Last slide. This is, it's got XLAM all over it, but it's more about, I actually generated this when I previously worked with Tilling Timber and KLH, and I came from a commercial construction background, and my first observation was that, guys, the timber industry needs to collaborate across the whole range of the design process and construction. You can't just be a designer, you can't just be a supplier, and you just can't be just an installer. Because at the moment, working in the commercial space, the timber industry haven't been able to collaborate across all of that. Now, it's almost like we just want to pick up a block of timber and say, there's your timber, We need to really grow, and it's really working well. A lot of businesses in the last 5 years have adopted this philosophy in the timber industry, us being one of them. So it's about collaborating all through that process. So it's about early stages, talking to someone about the design, helping them understand what the costs are for that, being able to supply it, but also being able to construct it. So the Kane Constructions job at Monash University, we did the design, the supply, and the installation as one package. Okay, and I'm pretty sure we're more expensive than anyone else, but the builder, that's what they wanted from a risk perspective. Okay, so it's really important to understand that project collaboration as well. So that's it. Thank you. And